Welcome to converting between rectangular and polar coordinates. So the general idea here is if we take advantage of right triangle trig, and the Pythagorean theorem, we can pretty quickly go back and forth between the two. So if you imagine a circle of radius r, and a point on that circle at angle theta, the x and y coordinates are essentially can be found using right triangle trig. So we have that cosine of theta would be x over r. We have sine of theta should be y over r. Okay. And then Pythagorean theorem would tell us that x squared plus y squared is equal to r squared. So we get a fairly useful formula to go from polar coordinates to rectangular coordinates. To go from polar to rectangular, if cosine of theta is equal to x over r, that means that x is simply equal to r times cosine of theta. Similarly, y is equal to r times sine of theta. So cos theta and sine theta are the coordinates on the unit circle, and then multiplied by r just scales us out to the correct position. To go from rectangular to polar, we have the r squared is equal to x squared plus y squared. So we can solve for r. And then we need to find theta such that cosine theta is x over r and sine theta is y over r. So again, we need both of those to be true because there are two positions on the unit circle that give the same cosine and two positions on the unit circle that give the same sine. So you have to find the one that agrees in both places. So for example, let's convert the polar coordinate 3 comma pi over 4 into rectangular coordinates. So in this case, we have our r is 3. Our theta is pi over 4. So that means that our x should be equal to r times cosine of theta is simply 3 times cosine of pi over 4. Otherwise known as 3 times root 2 over 2. Our y is r times sine of theta, or 3 times sine of pi over 4, otherwise known as 3 times root 2 over 2. And so we wind up getting our coordinates are 3 root 2 over 2, comma 3 root 2 over 2. Now let's go ahead and go the other direction. Let's convert the 0.25 into polar coordinates. So the 0.25, we have x is equal to 2, y is equal to 5. So we know that r squared is 2 squared plus 5 squared. So r would be the square root of 4 plus 25, or the square root of 29. Now we need to find theta such that cosine of theta is x over r, or in other words, 2 over the square root of 29. And we know 2,5. So we know if we think of the 0.25, this is in the first quadrant. And so specifically, we need to find theta that falls between 0 and pi over 2. So if I find my cosine inverse, that'll give me theta. So theta is cosine inverse of 2 over square root 29. Just a quick note. You may need to use your knowledge of right triangle trig to figure out, do you add pi? Do you do pi minus theta, etc.? So use your knowledge of the unit circle and quadrants. To determine if you use cosine inverse of x over r, or cosine matches with 2 pi minus that. So, or if we do 2 pi minus cosine inverse of x over r. Right. So again, the cosines is the x coordinate. They agree for sort of the negative version and positive version of the angle. But since we're looking between 0 and 2 pi usually, we can do 2 pi minus. Or the other option is to simply use negative cosine inverse of x over r. So for an example, let's go ahead and convert the equation y equals 3x squared into polar coordinates. So again, note that x is just r cosine theta. And y is r sine theta. So we simply have r times sine of theta is equal to 3 times r times cosine of theta, that entire r cosine of theta being squared. Or in other words, r sine of theta is equal to 3r squared times cosine squared theta. If you wanted, you could rewrite this as 3r is equal to sine theta over cosine squared theta. And that works for everything except where r equals 0. Possibly. So this is again a fairly straightforward technique here. So while when we were translating coordinates, it was going from polar to rectangular, where this formula came in handy. To translate equations, it's simple to go from rectangular to polar, right? So note, to translate an equation, from rectangular to polar, it's just substitution. With, again, x is the same as r cosine theta, and y is r sine of theta. It gets much more complicated when we want to go the other direction. So to convert the equation r equals 2 tangent of theta into rectangular coordinates, it's a little more complicated. So this is a little more complicated. In general, the trick is to look for r cosine theta, r sine of theta, and r. If we can't get r cosine theta or r sine of theta, then it's a little challenging. If we can find r, then we can use the r squared equals x squared plus y squared. So in this case, we have r is equal to 2 tangent of theta. This is the same thing as saying that r is equal to 2 times sine of theta over cosine of theta. We can rewrite this as r times sine of theta. Sorry, r times cosine of theta is equal to 2 times sine of theta. From here, if we now multiply by r, to force r sine theta. And so this would become r squared, or r times r cosine of theta, is equal to r times 2 sine of theta, or r times r cosine of theta is equal to 2 times r sine of theta. Again, r cosine of theta is our x. R sine of theta is our y. So we now have r times x is equal to 2 times y. Furthermore, we know that r squared is equal to x squared plus y squared. This means that r must be equal to either the positive or the negative version of the square root of x squared plus y squared. This gets a little tricky, therefore. We don't necessarily know which one we need to take. So one option would be just to essentially square everything and work with it there. So, or you could work with a square root. But, so essentially we have square root x squared plus y squared times x equal to 2y. This works whenever r is greater than or equal to 0. And then we would have negative square root x squared plus y squared times x equals 2y. And this works whenever r is less than 0. All right, so again, the idea here is that we are looking for essentially copies of r times cosine theta and r times sine theta. That's the only way really to get the x and y to appear, other than if we just have r involved. So this is how we can go about sort of translating back and forth between polar and rectangular coordinates, as well as between equations in polar and rectangular.